Okay, so today we're going to talk about volumes, which last time we did triangulations. So today we're going to use them to talk about volumes. And yeah, I paid great attention to triangulations having this property that two simplices have to intersect via their common face. But today we're going to kind of forget about this and just use the more naive notion of a triangulation. But anyway, let me first give a definition. So I'm going to consider normalized volumes. Normalized volume of a polytope. So let's say P is a polytope in R to the D. Then, by definition, the normalized volume is d factorial. Yeah, let me use n factorial times the usual Lebesgue volume of P. On Rn. And in particular, we discussed this a while ago. So let's say what is the volume of what is the normalized volume of the hypercube? Does anybody remember? 1. Interesting. 1 or n factorial, right? One of these should be 1 and the other one should be, yeah. So the usual volume is 1 and the normalized volume is just by definition n factorial because, well, this is 1, so this has to be n factorial. And what about the volume of a, so let's say we have an n-dimensional space. What about the volume of the, if I take the convex hull of all basis vectors, I get the d minus 1 dimensional simplex, n minus 1 simplex. So what is the volume? One over 2 to the n times 1 over factorial, or 1 over n factorial. That's interesting. So question mark 1 over n factorial. Any other versions? Yeah, 0. Maybe this is 0. Why would it be 0? Okay, nice. Yeah, that's actually true. So I'm using this n-dimensional volume measure on R to the n. So the n-dimensional volume of this simplex, which the picture looks like this. So a triangle in 3D has volume 0. Indeed, the answer is 0. Yeah, and but remember we had a different, yeah, and normalized as well. And we're going to talk later about how to make this work. You can project and then take the volume of the projection, but for now this is 0. And what about the, remember we had a different simplex. W sub W is the subset of x in Rn, where x w of 1 less than or equal x w of 2, etc. x w of n. What is the volume? What is the normalized volume of this simplex? 1 over factorial. Well, you have to multiply by, yeah, if I'm using then just 1. Okay, so that's nice. So this normalization actually, it sort of tells you the following thing, that the smallest, this is a simplex whose vertices are integer, have integer coordinates. So, and the smallest volume it can have is 0, of course, but if it's non-zero, then the smallest volume is 1. It has to be, yeah, there's actually, I mean, you can actually write it down for an arbitrary, for an arbitrary simplex. So yeah, let me even write it down. because this is sort of important point. So more generally, let's say I have a bunch of points, a0, a1, all the way up to an in R to the n. Right, so you have n plus 1 points in R to the n. And then I want to take the convex hull. So I want to take the simplex with vertices in these points. Then the volume of the convex hull of these points, a0, an, is, well, what is it? Let's say even the normalized volume. How do I find, for arbitrary n plus 1 points, what's the formula for the volume? Interesting. Yeah, nice. That's exactly right. So you take basically the determinant of the matrix A1 minus A0. These are the row vectors, or column, whatever. A2 minus A0, an minus A0. This is an n by n matrix, so you take the determinant, and well, this is going to be maybe negative sometimes. You take the absolute value, and then because we're taking normalized volume, you don't have to divide by n factorial here. It's just the usual determinant. So in particular, if all of these are integers, have integer coordinates, then this is going to be an integer matrix. So the determinant, like the smallest non-zero value is 1. And if in that case, let me make a definition. A unimodular triangulation is a triangulation into top dimensional simplices of volume 1. Okay, so you have a large polytope. You want to subdivide it. If you subdivide into simplices whose volume, each volume is 1, then the volume of the whole polytope becomes an interesting combinatorial number. This is the number, the normalized volume of P is just the number of such simplices. In particular, as I discussed last time, we had examples where we triangulated the hypercube into n factorial simplices. Each has volume 1, so the volume of that normalized volume of this thing is n factorial, which is the number of simplices, and the normalized volume of, if you remember, we also did the order polytope. Triangulate the order polytope, and then the answer was, what was the answer? Right, yeah, the number of linear extensions of your poset. So just counting the simplices, you get these interesting numbers. So now I want to do something slightly more complicated, and that's also related to what we did in the first lecture. So remember, or not the first lecture, but one of the first. We had a subdivision of the hypercube into hypersimplices. You take the hypercube 0, 1 to the n, and then it was a union of these delta prime hypersimplices. union delta prime 2 comma n plus 1 etc. delta prime n comma n plus 1. And the definition of each of them, delta m k comma n plus 1, is the set of points in the hypercube. It's the slice where the sum of coordinates is between k minus 1 and k. All right, do you remember? Yeah, there was a picture. I had a picture. Picture is that the hypercube was subdivided into two hypersimplices like this, and then n equals to 2, n equals to 3 is the usual cube. It was subdivided into, if you take these sections here, then it is subdivided by these sections into 3 slices. And so these slices are delta prime 1 comma 3, delta prime 2 comma 3. These are delta prime 1 comma 4, prime 2 comma 4. Right, the tetrahedron, octahedron, and the upside down tetrahedron. Okay, so it is a union like this, and then there is no, they don't really overlap in the interiors. So as we discussed, the volume, let's say the normalized volume of the hypercube is the sum of the normalized volumes of delta prime k comma n plus 1. Okay, and this, we know this is n factorial. So the question was, the motivating question was, what are these numbers? I'm going to tell you that they are integers, and so there's a bunch of integers that sum up to n factorial. And in the case of the square, for n equals to 2, this is going to be equal to 2, and each of these is going to have volume 1. And for n equals to 3, we had 6, which is equal to, what are the normalized volumes in this case? One, 1, 4, 1. Right. Okay. 1, 4, 1. Yeah. You can triangulate the octahedron into 4 simplices, and I guess one way we discussed this is in the last lecture when we were trying to come up with non-regular, with non-triangulations. Yeah, there was an example with the octahedron and 4 tetrahedra. Yeah. Anyway, so this is 1, 4, 1. And so question is, what is in general? What happens, say, 24 should be equal to question mark plus question mark plus question mark plus question mark. What are these numbers going to be? What do you mean by special inversion? Nice. Yeah. Okay. So it's a natural conjecture, because we've seen these numbers, right? For n equals to 1, n equals to 1, I get 1 is equal to 1. So this triangle of numbers looks like, starts as the same way as the triangle of Eulerian numbers, which are, I mean, in this case, you would get 1, 11, 11, and 1, and etc. And remember, so each Eulerian number is the number of permutations. A of n comma k minus 1 is the, well, n comma k is the number of permutations w in Sn, which have exactly k descents. Okay. So And where did we see these numbers? What do these numbers, how did they appear previously in our class? Okay, h vectors of what? Simplices. Actually, no, for simplices it was just one, the h vector is 1, 1, 1, 1, 1. Right, okay, so these numbers give you, nice, they give you the h vector of the dual of the Bermuda-Hydron. And actually, yeah, it's going to turn out that the volumes are given by the same numbers as the h vectors of the Bermuda-Hydron, and I have no idea why this should be true. Yeah, this is a complete, to me, that's a coincidence. If anybody has like a deep explanation, please let me know, because I looked it up and yeah, nothing. Yeah, anyway, so that's a theorem. That's a theorem which, yeah, by the way, let me, right, the Bermuda-Hydron is the Minkowski sum of these same polytopes. That is true. And yeah. Probably not. Yeah, I know. It's, yeah, if you have any generalization of this to, yeah, that's the only case where I don't know, the h vector, yeah, that's crazy. But it's true. So that's a theorem which is due to, I mean, apparently Laplace in 1886. And the theorem is that the normalized volume of delta prime k comma n plus 1 is, so remember, Eulerian numbers were invented in, I think, 1755 or something like this. So there was like more than 100 years between the two discoveries. But anyways, the volume is just the Eulerian number of n comma k minus 1. And all right, so how do we prove this? Oh, interesting. You want to find a poset? Yeah, I never thought of this. I didn't know such a poset. No, but it's a good idea. So yeah, you wanna, because yeah, the ordered polytopes, right? So the cubes and the ordered polytopes are triangulated into these simplices of the form nabla sub w. And yeah, so you want to find, maybe you want to find a collection of such nabla simplices which together triangulate the hypersimplex, because it's a subset of the cube, right? And we know the cube is triangulated into those, so maybe we restrict. And does that work or does that not work? What we want to do is triangulate the cube, well, the hypersimplex, k n plus 1, into these unimodular simplices. The question is, how do we do that, and can we do that? And Have to intersect what? Ah, interesting. So you're saying, yeah, actually, yeah, if we look at this picture already, right? Yeah, there is a problem. There is a problem, which is that let's say 0, 1 squared. I mean, you're absolutely right. So if I take, for example, the cube, then these are the nabla simplices. Nabla 1, 2, nabla 3. But these are the hypersimplices. So nice. So you wanna find a certain transformation of the whole cube that would take it from here to here. And actually, yeah, if we look, indeed, if we look at these simplices, right, this is just the relative order of the coordinates. So if we look at the cube, this is the origin, 0, 0, 0. So in the neighborhood of the origin, there is each of those simplices appears covers some subset of the neighborhood of the origin. And here, 1, 1, 1, you also get all of those simplices. So they kind of they intersect every slice. And moreover, I mean, if you try to rotate, if you try to somehow apply some change of basis, then you see that the first slice does not intersect the third slice. So if you try to triangulate, I mean, they are kind of far away from each other. But all of those simplices they have points which are close to each other. So it looks like this shouldn't work. This goal doesn't really work. And yet somehow there's a certain transformation which is not an affine transformation that somehow works. So here is a proof which was constructed by Stanley in 1976. And so here is the transformation, which again is going to look very weird, but so consider a map C from the hypercube to itself, which is given by the following transformation. So you start with x1, x2, all the way up to xn, and you send them to y1, y2, yn, and the formula for the new coordinates is gonna be yi is equal to either xi minus x I plus 1, or to xi minus, it should be xi minus 1. It's xi minus 1 plus 1. Yeah, so I want the result to be between 0 and 1. So this happens if xi minus 1 is less than or equal to xi. And this happens if xi minus 1 is quickly bigger than. And the way for you to think about this map, I mean, I defined it on the whole hypercube, but you should think of it as really being defined on the interior of each nabla simplex. Or, yeah, I haven't discussed this yet, but let me, yeah, anyways, when there is equality between two adjacent numbers, I have a choice. It's discontinuous at those points. Yeah, let me first write down what's the inverse map. How do I write xi in terms of y? Say it again. Okay, yeah, so you're saying, well, yeah, after identifying R mod z with 0, 1, this is basically, yeah, I'm taking the difference and then taking it modulo Okay, so yes, okay, so you're saying that modulo z, modulo z xi is just, here, by the way, I is goes from 1 up to n, and we assume that x0 is 0. So the first one, you have to subtract 0. So you want to say that modulo z xi is y1 plus y2, etc. plus yi. Right? And then we also know that xi is between 0 and 1. So the actual answer is y1 plus etc. plus yi minus the fractional part. Okay. I mean, these two conditions determine exactly, well, almost exactly. You have to choose between 0 and 1, but again, I'm not going to worry about these exceptional cases because I want to compute the volume, and the volume doesn't really care about me being any bad behavior on codimension 1 subspace. Yeah, okay. So so two properties of this map. First one is that wherever it's defined, it's volume preserving. A is volume preserving on each, well, and linear on each nabla sub W, or yeah, on the, let's say on the interior of each sub W. Right. So whenever we know that any two coordinates are not equal to each other, then you can just read off which one of these formulas you use from the permutation. So the permutation tells you the relative ordering of the x's, and you know a formula for yi which does not include any cases. And second of all, let's say I give you a nabla simplex, and then I compute, then I apply my map to the nabla simplex. What is going to be the sum of coordinates? How do you, I mean, I take the x, take an x in this polytope, and then I compute the y's, and then I want to see which hypersimplex, right, which of those slices does the y point belong to. How do I do that? Ah, nice. Right, so if you analyze this formula, then what you see is that you add +1 whenever there is a descent in your permutation. Right, and then the rest of the sum kind of telescopes. Yeah, let me actually write it down. So yeah, let's what is the sum of coordinates of this thing? And the sum of coordinates is even the sum of coordinates is you take y1 plus etc. plus yn, and then just use that formula. So you have x1 minus x0, maybe, well, actually x0 is 0, so you always use this formula. And then you have x2 minus x1, maybe +1, sometimes +1, depending on w. x3 minus x2, maybe plus 1, etc. xn minus 1, maybe plus 1. And so if you sum up just the x's, then you get just xn and minus x0, which is 0, plus basically the number of descents of w. Or of w inverse. Yeah, I don't either w or w inverse isn't here. Does that make sense? Right. And that's basically the whole proof. Any questions so far? Yeah, and by the way, so here I wasn't very careful about what happens when it's discontinuous, right? It's, at some point it's discontinuous, but let me claim that the collection of the simplices that you get, so exercise, exercises that the resulting collection of simplices, yeah, let me call them, you just take P of nabla, W, and then you take the closure. Yes, so you think of P as being defined on the interiors of simplices, but then you take the closure, get actual simplices inside the hypersimplicity. Is an honest triangulation of the hypersimplex. So this exercise includes that even though for the volume computation we didn't need this, actually the resultant simplices intersect properly. Every intersection is a face of both of them. And so before I did the cube, the ordered polytope, the hypersimplex. There is the permutation, right? Yes, one question for you is what is the volume of the permutahedron? Any guesses? Is it also 0? Nice. Yeah, this is 0. But okay, so what is the n minus 1, whatever that means? N minus 1 dimensional volume of the permutahedron. And that's actually a number. And you have to normalize it in some way to make integer and nice. But any guesses? Right, so for a proof, you would need to partition it into simplices. But how would you do that? That's okay. It's the Minkowski sum of simplices. But then, how do you write a volume of something? What's the volume of the Minkowski sum of two polytopes in terms of the volumes of the original polytope? And that's actually, I mean, that depends on the orientations of the two polytopes. And you can even have, it's also Minkowski sum of line segments. Yeah, actually, I mean, this is a hard question, but we're going to discuss this in detail. Let me just mention a spoiler. The volume is going to be n to the n minus 2. Reason? It's some normalized n minus 1. Yeah, I have to define an n minus 1 dimensional volume correctly. But after I do it, it's to the n minus 2. In particular, yeah, it can be subdivided into actually this many. This is not the normal. Yeah, this is the. Yeah, but I have to specify the I have to normalize it so that I know that, like, yeah, basically this is the unnormalized volume. So in that plane, I have cubes. I want them to have volume 1, and then this is going to have volume, yeah, it's going to be subdivided into n to the n minus 2 cubes. Right, that's there's Cayley's theorem. This is the number of spanning trees of the complete graph. And in fact, yeah, we're going to do this for arbitrary graph. For arbitrary graphs, there's something called the graphical zonotope, and then the volume is going to be the number of spanning trees. But anyways, I'm getting ahead of myself. Yeah, any questions so far? All right, so here's the question. Does every polytope P admit a triangulation? Clearly, triangulations are useful for computing volumes. So if I give you a polytope, is it easy to find a triangulation? With what definition? No, just arbitrary. Yeah. Yeah. Forget about the not necessarily unimodular triangulation. I see. So you wanna take a polytope, remove one vertex, and triangulate the rest, and somehow add this vertex and add an extra triangulation of the. Yeah, I think that would actually work. Yeah, I think this should work. But I guess the answer is yes. But let me tell you another easy way to construct a triangulation. So every polytope admits a triangulation, and even a triangulation without new vertices. So, and let me even do this more generally. So I want to, this is sort of a transition for us, because before I was talking about polytopes, now I'm going to start slightly moving away from polytopes and talking about other things. First of all, I'm going to try to, here is the more general situation I'm going to consider. So definition, let's say A is a point configuration, just finite set of points. You can think of A as vertices of polytope, but it need not be, they need not be in convex position. Finite point configuration. Then I want to consider triangulations of A. And just by definition, a triangulation or a subdivision of A is a subdivision C of the convex hull of A. Yeah, let me denote this of the polytope, which is the convex hull of A. Right, and then the extra condition is that the vertices of the subdivision should be contained inside A, such that the vertices, the zero-dimensional elements of the subdivision, are contained inside A. Previously, I was kind of vague about whether your triangulations include you're allowed to add any new points or not. Here, I'm actually restricting the new vertices to all lie in A. So you're allowed to use vertices of A, but not any other vertices. Example is if you give me a bunch of points, maybe this is A, then I can come up with a subdivision. So it has to be every element of the subdivision has to be a polytope. So I want to subdivide the convex hull of A into convex polytopes, but I'm allowed to use A's also has this vertex, but I don't use this vertex. I'm allowed to not use some of the interior points of A. So now I can ask the same question, like what does every point configuration admit a triangulation? And this is sort of tricky. Because I don't know, maybe it's not tricky. Maybe it is tricky. Maybe the same proof works, maybe not. Seems like it should work. Maybe it doesn't. Yeah, anyways, I'm gonna tell you actually a different construction. So I'm gonna start with an arbitrary collection of points in the d-dimensional space, and then I'm gonna give you a bunch of very nice triangulations of that collection of points. And that is the next subject is regular triangulations. Right, yeah, that's a good question. What if all my points lie on the same line? Right, so let's try an example. Let's say I take 3 points on the line. This is my A. So yeah, how many triangulations does this point configuration have? 2. Which ones? Nice. Okay. 1, 2, 3, and 1, 3. Yeah, okay, these are the 2 triangulations. And we're going to actually generalize this example to all dimensions. Yeah, n plus 1 points in n dimensions. It always has 2 triangulations. Yeah, but yeah, it's natural for me to consider both of these as triangulations of my point configuration. And in general, yeah, you can take arbitrarily many points and then try to figure out what's the number of triangulations on the line. That's a good exercise. So yeah, regular triangulations. You give me an A, and I give you plenty of triangulations of A. And the idea is the following. Say A is a point configuration, finite set of points. And what I want to do is I want to choose any, doesn't have to be linear or anything, just any function. Any function h from A to R. And then, so for x in A, I want to define x tilde in R to the d plus 1 be given by, so x tilde, it has the first d coordinates are as in A, and then the last one is h of x. So for each point in A, I want to lift it into the d plus 1 dimensional space using my function h. And I'm going to draw a picture in a second, but for now, let p tilde be the convex hull of x tilde, where x runs over the points of A. Okay, so let me try to draw the picture. I'm going to go backwards. maybe my point configuration, here's my r to the d, and then maybe my point, yeah, let me just take a picture. Maybe my point configuration A looks like this. Maybe it's a triangle with a point. This is A. And then, so I choose a function h, which means I'm going to lift every point. I'm going to lift every point to some height. And this is going to be my x sub d plus 1. Lift every point to some height. And then I take the convex hull of the resultant points in d plus 1 dimensions. And this red polytope is p tilde, which, you know, it depends on h. Yeah, I mean, p tilde sub h, we should call it. P tilde sub h. Or I could, you know, I could start with the same point configuration. And I could lift the points in different way. Maybe have them like this. And then this one goes here. And then my polytope would look like this. This would be p tilde. So the idea is, yeah, and I'm going to explain this rigorously next time. But the idea is to, the way you're going to get the triangulation of A, you're going to take p tilde and you're going to take only the lower faces of p tilde. And I have to explain what is lower faces, but here this has three, this polytope has three lower faces and this one has only one. Lower faces is are the ones you can see from the plane if you look up. But yeah, I'm going to explain this rigorously. And anyways, if you just take the lower faces and you project them down, here you're going to get a triangulation A, which looks like this. And here you're going to get a triangulation of A, which looks like this. And such triangulations are going to be called regular. And yeah, I'm going to prove that each of them is a triangulation, and then it turns out, it's going to turn out that these have very nice properties. So yeah, I think that I'm out of time. So thanks everybody, and have a good weekend. See you all on Monday. Thanks. Right, in general, H has to be generic. Then you get a triangulation. If H is non-generic, you still get a subdivision. So it's just not going to be into simplices.